Hello and welcome to part 2 of our Juniper Learning Byte, where we discuss switching basics on EX series switches, paying particular attention to the spanning tree protocol and discussing why it is important in today's modern networks. Before we do, we're going to look at a very basic design of a LAN. And in this LAN we have sort of 4 switches connected to each other via gigabit uplinks. And on each switch we have a workstation. Now, this network is fine, it'll work very well. However, let's say that switch 1 should fail. Well, what will happen is, switch number 3 becomes isolated, and workstation 3 can no longer communicate with workstations 2 and 4. To correct this, we can add an extra link. So we add a link between switches 3 and 4. So that should switch 1 fail, switch 3 can communicate via switch 4.
Now this extra link has actually introduced a small issue. Now, give you an example of this. Let's say that workstation 1 wishes to communicate with workstation 3. So it sends a frame, destination MAC address of workstation 3, and switch 1 will send it on the network. Now, let's say that actually what's happened is workstation 3 has just gone down, it's just died, or it's not available. Well, in this situation, as we discussed before, this frame will be flooded out of all ports except the port it came in on. Therefore, this will be sent to switches 2 and 3 via the uplinks. Now, switches 2 and 3, they have no idea, again, where this workstation is, so it will send them to switch number 4. Now switch number 4, we'll look at these, and it will treat them as 2 separate broadcasts. So what it will do is send them back out to switches 2 and 3. Now, with frames and switching on a network, there is no time to live like you'd have in a router. So this will basically just keep spinning round and round the network. You'll keep going round the links back to switch 1. Eventually, all the bandwidth on the uplinks will be consumed. And what will normally happen is the network will then crash. So this scenario where traffic is looped around the network is actually called a bridging loop. And most modern switches have a mechanism whereby they can help prevent these bridging loops. And this mechanism is called the spanning tree protocol. Now with this, what happens when a switch first powers up, it starts sending special frames on the network called BPDUs. It sends them off to its nearest neighbours. They will process it, and in turn tell the neighbours that they are available and a switch. Using this, each switch can build up a topology of the network so it knows exactly where every switch is and where a bridging loop is likely to occur. So in this case, switch 4 has realised that there is a bridging loop, and it makes a decision to block its uplink to switch 3, thereby preventing the loop. However, let's say that we have a link failure. So, in this scenario, the uplink between switches 1 and 3 has been blocked by a spanning tree automatically. But for some reason, the uplink between switches 2 and 4 is then cut, or severed, or maybe disconnected. What can happen is notifications sent around the network, and the uplink between switches 1 and 3 is then brought back into use. However, with the original version of spanning tree, or 802.1d, this recovery could actually take up to 50 seconds, which in today's modern networks is actually a lifetime. So, to remedy this, the IEEE came up with what we call rapid spanning tree. And in the event of a failure, the recovery should be almost immediate. This particular version was called 802.1w. Now, there is also another issue. We have these, again, these uplinks being used, and we have one that's being blocked. All traffic will be using exactly the same links. So in this scenario we have VLANs 10 and VLANs 20. Now this is a bit wasteful, because you've got a link at the bottom, a gigabit uplink, that's not been used at all. So the IEEE introduced multiple spanning tree, and this allowed you to run VLANs across one link and other VLANs across another link. So in this scenario we have VLANs 10 running across the link between switches 1 and 2, and VLAN 20 is running between switches 3 and 4. This particular version was called 802.1s. So what we're now going to do is have a quick demonstration on how to configure and monitor spanning tree protocol within Junos. So the first thing we'll do is check which version of the spanning tree protocol is running. We're going to check the status of it. Then we're going to remove whatever the default spanning tree protocol is, and then configure 802.1s multiple spanning tree instead. Then we'll look at the status once more to see how the output differs. So we're now back on the command line of our EX series switch, and from here, if we enter the command show spanning tree, you can see we have 4 options. And the first one, bridge, will show us how spanning tree is configured, and more importantly, which version or type of spanning tree we're running. And in this case, this is rapid spanning tree. Now this switch has just been powered up, it's just been configured, which means by default EX series switches would use the rapid spanning tree protocol. Now we can also, if we enter the command interface, this will show us which interfaces are running the spanning tree protocol. And if we then go to statistics, we can say interface, and this will show us how many BPDUs have been sent or received. At the moment this network is actually quite quiet. So as we've seen, we are running the rapid spanning tree protocol. What we'd like to do now is change it to the multiple spanning tree protocol. And to this we would go into the configuration mode, edit protocols, and then under the protocols you will see we are running RSTP. So if we say delete RSTP, and we say set MSTP, we should see the MST protocol is now enabled. Only with the MST protocol you do have to do a little bit more configuration than what you would do with the standard or the rapid spanning tree protocols. So if we then edit MSTP, then set, and here we have multiple options. Several of these are required for this to work. And the first one would be the configuration name. Now in this one we're going to call it Acme. You can obviously call this whatever you wanted to, but every switch that has this name will then be part of the same multiple spanning tree domain. In theory you could have multiple spanning tree domains on your network, but in this case we'll have just one. So now we set the configuration name. The next thing we would do is set the revision level. Now this would be used if you are configuring your network and you want to separate 2 different revisions until you finish the configuration. So if we say set revision level 1, so now the database is set to revision level 1. Then finally, the way multiple spanning tree works is it will run several different instances of spanning tree, and this is how it then divides the different VLANs into the different spanning tree domains. So on this case we will then say set MSTI, and we will give it an ID. In this case you can have up to 4094 instances of multiple spanning tree running. But in this case we will have one for VLAN 10 and one for VLAN 20. So if we say set MSTI 1 and then VLAN, and we will say finance. Then we'll set MSTI to VLAN marketing. In theory, that's all we need to do. So, if we now commit this and look at the spanning tree bridge information, we can now see that the enabled protocol is certainly MSTP. We can also see at the bottom of the screen we are running the two instances, so MSTI 1 and 2. These ones we created and assigned VLANs 10 and 20 to them. Then we have another one at the top that says CIST. Now this is the common instance, and any VLAN you've not added to the other instances manually will automatically be added to the common spanning tree instance. Now if you want a bit more information about which VLAN has been added to which instance, if we say show spanning tree MSTP configuration, we can now see that MSTI 1 is VLAN 20, MSTI 2 is VLAN 10, which is the marketing and finance VLANs. So to summarize, we discussed that if a bridge and loop should occur on your network, it can have absolutely disastrous effects and could bring your network down. But the spanning tree protocol was developed to prevent this from happening in the first place. We also discussed that the original spanning tree protocol, or 802.1d, took up to 50 seconds to converge, so the rapid spanning tree protocol was developed to offer a much faster convergence mechanism. Then we discussed how the multiple spanning tree protocol can then make use of links that would otherwise be blocked. Unfortunately, this brings us to the end of our learning byte. I hope you've enjoyed viewing, and I hope you found it informative. Look forward to seeing you again in the near future. In the meantime, thank you for viewing.
Visit the Juniper Education Services website to learn more about courses. View our full range of classroom, online, and e-learning courses. Learning paths, industry segment and technology-specific training paths. Juniper Network's certification program, the ultimate demonstration of your competence. And the training community, from forums to social media. Join the discussion.